This is chapter 15, number 24, and 24 states, a cart attached to a spring with constant 3.24 newtons per meter vibrates with position given by x equals 5 centimeters cosine of 3.6 t radians per second. Now, on A, during the first cycle, from t equals 0 to t equals 1.75 seconds, just when is the system's potential energy changing most rapidly into kinetic energy? And B, what is the maximum rate of change of the energy of transformation? Now, first we want to list our givens. Our givens are 3.24 newtons per meter. That's the K value of the spring. We are given that x equals 5 centimeters cosine of 3.6 t radians per second. That's the position formula for the spring. And we're given the time between 0 and 1.75 seconds. So what we want to find is we want to find the t, where the potential energy is changing most rapidly, and we want to find the derivative of the potential energy. Now, first we want to solve for the potential energy. The potential energy is equal to 1/2 kx squared, and which is also equal to 1/2 k a squared cosine squared of omega t. Now, this is the formula that we'll use to solve for the position. The rate of change of the potential energy is the derivative of potential energy, which, shown here, the derivative simplifies down to negative 1/2 k a squared omega sine of 2 omega t. This is the rate of change where we have to find is maximal and negative at 2 omega t pi over 2. And any recurring value 2 pi greater than that, which the general formula for that would be 2 omega t equals 2n pi plus pi over 2, and for any integer value n after that value. We'll only focus on 0 and 1 in this case. In this case, t equals pi over 4 omega, 4n plus 1, and this form it will simplify down to pi 4n plus 1 over 4 3.6, and 3.6 is the omega value. With this formula, when n equals 0, we are given that t equals 0.218 seconds, and when n equals 1, we find that 1.09 is equal to t. And for all values of n, after this, they're outside the specific range of the time, so they're not needed. For part B, we have to take the absolute value of the derivative of potential energy. And so the formula we saw above simplifies down to 1/2 k a squared omega. And so if we plug in our values for k, for a, and for omega, this simplifies down and we get the equation. The answer is 14.